Hello everyone. In the last lecture, we discussed about the space quantization. We saw that the diatomic molecule cannot arbitrarily orient itself with respect to the reference axis, but the molecule can only orient itself in certain directions. If one molecule is in the jth quantum level, so let us say the molecule is in the jth level, then there are 2j plus 1 possible orientations. So, 2j plus 1 possible orientations, and these orientations all have the same rotational energy. So, for example, when j equals 2, we know mj equals minus 2, minus 1, 0, 1 and 2. So, we can see in this figure, so mj can take values of plus 2, plus 1, 0, minus 1 and minus 2. So, we can say that j equals 2 is 5-fold degenerate. So, the jth level is 2j plus 1 fold degenerate, or we can write the degeneracy Gj equals 2j plus 1. Because we have looked into space quantization in the last lecture, today we will start by looking into the consequences of space quantization. There is an additional selection rule associated with mj, and this additional selection rule associated with mj is given by delta mj equals 0 plus minus 1. That means, the change in the mj quantum number must be equal to 0 or plus minus 1. However, as the energy of the rotational level does not depend on the quantum number mj, this selection rule delta mj equals 0 or plus minus 1 has no effect on the rotational spectrum, as the molecule does not know what the z axis or this arbitrary axis or the reference axis is. Now, the question is, when can we have an exception of this? We can have an exception if the molecule is not in an isotropically even spatial environment. If somehow the molecule knows what the reference axis is, the result would be different. But how can the molecule know the direction of the reference axis? This can only happen if an electric or magnetic field is applied externally in a particular direction. If an electric field is applied in a particular direction, there will be an interaction between the electric field and the dipole moment. This interaction depends on the spatial orientation of the molecule. So, the energy of the system will now depend on the mj quantum number, and the selection rule with regard to mj, that is delta mj equals plus minus 1, will affect the rotational spectrum. Thus, the degeneracy will be lifted, and this lifting of degeneracy in the presence of an externally applied electric field is known as Stark effect. So, let us say j equals 7. So, there will be 2j plus 1, that is 2 times 7 plus 1, that is 14 plus 1 or 15 possible levels, which will all be degenerate in the absence of the externally applied electric field. In the presence of the electric field, the degeneracy is partially lifted, and the selection rule delta m j equals 0 or plus minus 1 becomes important. Each level now splits into j plus 1 components, such that the absolute value of m j can be either 0, 1, 2 or integral values up to j. So, we can see this in this figure. When the field is off, all the states are degenerate. However, when we turn on the field or we apply the external electric field, then the degeneracy is partially lifted, and we can say that for plus 7 or m j equals plus 7, mod m j equals 7. Also, mod m j equals 7 for m j equals minus 7. So, when the molecule is at m j equals plus minus 7, it is here. These are the levels for plus minus 6, and the highest level is for m j equals 0. The energy of any level now is given by E, which is now a function of both the j quantum number and the m j quantum number, and this is given by B times j plus 1 h c plus A, which is a function of j quantum number and the m j quantum number, the dipole moment mu squared and the electric field squared. So, this A term has some complex dependence, but before we go there, we see that the first term that we have, this first term is actually the term when the field is not present. This is because we know nu bar j is given by B times j plus 1. So, we also know the energy, if we express the energy in joule, then E equals h c nu bar. In other words, I can write E j equals B times j plus 1, which is nu bar j times h c. So, this first term was already there in the absence of the field. So, we have an additional term here, which depends on the electric field strength, on the dipole moment, and another parameter which itself depends on the quantum numbers j and m j. And the dependence, as we can see here, the A term depends on j and m j in a complex manner, but we do not need to care about this complex form of dependence, but as the energy depends on the dipole moment of the molecule, this is a useful way to measure the dipole moment of the molecule. We should remember that spectroscopy is done just not to obtain a spectrum, but to use the spectrum to determine something about the molecule. The Stark effect can be used to precisely determine the dipole moment mu of the molecule. So, now we will focus on the intensities of the rotational lines. The spectral line intensity is controlled by two things. Number 1 is the transition probability, which can be estimated from quantum mechanics, and the other is the population of the initial state, that is the population of the initial state from which the transition will take place. The 2j plus 1 degeneracy is going to affect the second thing, that is, it is going to affect the population of the initial state. If degeneracy is more for a particular level, the molecule has more chances to have that energy. So, therefore, more molecules are in that level. If we calculate the transition probability for a rotational system from quantum mechanics, we will see that the intrinsic probabilities of transition between any two adjacent rotational levels are identical. And here we are talking about adjacent rotational levels, because we know in the absence of any externally applied electric field, the selection rule says delta j equals plus minus 1. So, we can largely ignore the quantum mechanical effect of change in probability. So, the intensities of the spectral lines will be directly proportional to the number of molecules in each rotational level. So, we can imagine that as the spectrum is recorded over an ensemble of molecules, the molecules are distributed over different energy levels, or we can think the molecules are distributed over different values of j. The populations of these levels are governed by Maxwell-Boltzmann distribution. So, from Maxwell-Boltzmann distribution, we can write the population of the nth state divided by the population of the mth state equals degeneracy of the state n divided by degeneracy of the state m, that is the ratio of the degeneracies, times an exponential term e to the power minus delta E by k t. So, here G is the degeneracy, and this expression relates the number of molecules in the two states, the state n and the state m. So, the ratio of the number of molecules in the two states depends on the ratio of the degeneracies of the two states. So, if G n is greater than G m, more molecules will be in the n state. In addition, the ratio of degeneracy is multiplied by an exponential term e to the power minus delta E by k t, where delta E is the energy difference between the n and the m state, and the k t is the amount of thermal energy available to excite the molecules in any of the excited states. So, let us see how degeneracy is going to affect the population of the distribution. It makes sense to reference the population of any state to the ground state. So, here instead of referencing the population of the nth state to the population of the mth state, we can think about referencing the population of the nth state to the population of the ground state or j equals 0. This is because at j equals 0, m j can only take the value of 0. That means, j equals 0 is not degenerate. So, as j equals 0 is not degenerate, the degeneracy of the denominator, that is G m, disappears. So, let us consider two states. One state is j equals j and the other is j equals 0. So, we can write n j by n 0 equals g j by g 0 e to the power minus delta E by k t. So, we can write this as g j, but g 0 is 1. So, we can write g j e to the power minus of E j minus E 0 in brackets by k t. So, we also know that the energy is given by B times j plus 1 h c. So, for j equals 0, E 0 equals B times 0 times 1 times h c, that is 0. So, E 0 equals 0, and we also know g of j equals 2 j plus 1. So, we can write this as n j by n 0 equals 2 j plus 1 times e to the power minus E j by k t. Again, E j equals B times j plus 1 h c. So, we will write n j by n 0 equals 2 j plus 1 e to the power minus B h c j times j plus 1 divided by k t. So, now if you carefully look into the right hand side, we have to consider two terms. One is that of this 2 j plus 1, and the other is this exponential term. As j increases, 2 j plus 1 increases, or the degeneracy increases. But on the other hand, the exponential term decreases because of the negative sign. So, we have two competing terms. In other words, degeneracy indicates more molecules in the high j level, but the exponential term indicates fewer molecules as j increases. So, there will be a balance between these two terms. At some value of j, we will have a maximum population denoted by j max. So, if we look into this figure, here we are plotting 2 j plus 1, and we can see the steady increase of 2 j plus 1 as the j increases, and this red curve shows the plotting of this exponential term e to the power minus delta E by k t, which also decreases. And because there is this competition, we find a balance, or at some value of j, that is j max, there is a maximum. So, that 2 j plus 1 factor increases with j, whereas the exponential term rapidly decreases. So, we can see the 2 j plus 1 increases, the exponential term rapidly decreases. So, we can see that 2 j plus 1 factor increases with increase in j, and the exponential term decreases with increase in j. So, at low j, the 2 j plus 1 term makes this increase in this blue curve, but until at higher j, the exponential factor wins and n j by n 0 approaches 0. So, we can appreciate this by doing some simple calculus. We can simply differentiate the expression with respect to j. So, when the expression or d n j by n 0 d j, this is the gradient and this gradient equals 0 at the maximum or at j equals j max. So, the population therefore shows a maximum at a value of j equals j max, which corresponds to d n j by n 0 of d j equals 0 at j equals j max. So, if we solve this, if we solve this particular equation, we can get the value of j max and we can see j max equals root over k t by 2 b h c minus half. Now, if we put the values, for example, if we put the Boltzmann constant k equals 1.38 times 10 to the power minus 23 in the SI units, and we put h equals 6.626 times 10 to the power minus 34 in the SI unit, and the value of c if we put 3 into 10 to the power 10 centimeter per second, then what we will get? We will get this expression we can simplify as 0.5892 root over t by b minus half. The j max in the expression is a non-integer, but it has to be an integer because j max is some value of j and j can only take integral values. So, this non-integer value of j max happens because when we differentiate, we assume j is continuous, but this is not true as j is always an integer, or in other words these levels are quantized. The maximum line intensity should be the nearest j value or the nearest integral j value obtained from the above equation. I mean this particular equation that we have solved here. So, for example, for carbon monoxide CO, the value of B is 1.9225 centimeter inverse, and this value is at 298 Kelvin. So, if we solve this expression, we will find j max equals 7.3. So, the nearest integral value of j max or the nearest integral value of 7.3 is 7. Thus, we can say the transition from j equals 7 to j equals 8 will show the maximum intensity. But more importantly, j max depends on temperature. So, now let us have a closer look in the intensities or how will a rotational spectrum look like. So, here in this figure we have a rotational spectrum. So, if we know the value of B from the spacing between the spectral lines, because the spectral lines are spaced out by 2B. So, if we know the value of B from the spacing and also can identify the line which has the maximum intensity, that is, this is the j max line, or at this value the population or the spectrum has maximum intensity. So, you can use this information to determine the temperature of the sample. So, in this particular figure we see we have transitions 0 to 1, 1 to 2, 2 to 3. So, we can see J equals 2 gives the most intense line in the spectrum, and that means the transition which is most intense is coming from 2 to 3 transition. So, we can use this to determine the temperature, but we can think in the lab it is not helpful, as we can measure the temperature in a much easier way. We can just use a thermometer. But what if the molecule is in the atmosphere or even further away in space? In that case, these intensities of the spectral lines can be extremely useful to determine the temperature. So, now we will look into a couple of problems before we end this lecture. So, the first problem we have, so we have actually discussed a part of it during the lecture, but we did not do the entire derivation. So, we know n j by n 0 is given by 2 j plus 1 exponential minus b times j plus 1 h c by k t. So, we have to show, or we have to get to the final expression that we discussed in the lecture. So, we know that d n j by n 0 by d j at j max equals 0. So, let us try to evaluate from this expression d n j by n 0 divided by d j. So, for this we have to get that the derivative of first term, that is 2 times the exponential term minus b j times j plus 1 h c by k t, and then we have to keep this term constant, that is 2 j plus 1, and take the derivative of the next term. So, that we have exponential minus b j times j plus 1 h c by k t, and then we have j here, we have to take the derivative of this. So, that is times minus b h c j times j plus 1 divided by k t. So, this the left hand side we know equals 0. So, 0 equals 2, we can take the exponential part common, that is e to the power minus b times j plus 1 h c by k t. So, we have 2 minus 2 j plus 1 . So, here we have to take the derivative. So, this will be 2 j plus 1. So, we have 2 j plus 1 squared b h c by k t. So, we can write 2 j plus 1 squared times b h c by k t equals 2, or we can write 2 j plus 1 squared equals 2 k t by b h c, or 2 j plus 1 equals root over 2 k t by b h c, or 2 j equals root over 2 k t by b h c minus 1. So, from this we can get j, and because we are solving this at j equals j max. So, we can write j max equals root over k t by 2 b h c minus half. So, we have come to the expression that we needed to derive. So, now let us look into the next question. So, for HCl the value of B is given, the B is 8.5 wave numbers. So, the question is the most populated rotational state for HCl. We have 4 options: j equals 1, j equals 3, j equals 5 and j equals 7. So, we know that the j max, that is exactly what we need to find out here, is 0.5892 root over T by B minus half. So, we can write 0.5892 root over temperature. The temperature here is 300. So, 300 by B, that is 8.5 minus half. So, that becomes 0.5892 times 5.9409 minus 0.5. So, this becomes 3.5003 minus 0.5. So, this is 3.0003. So, the answer, which is the nearest integer, that is j equals 3.